But welcome, ladies, gentlemen, and non-binary to our Würth Elektronik webinar. My name is Amelia Thompson, your host for all things magical webinars presented by Würth Electronics. Now, I'm very excited about today's webinar. We have a newcomer. Nick Amy is the Director of Engineering at IQD. IQD is our sister company and the powerful creators of all things crystals and oscillating products. So we are very thrilled to have him here today. Today's webinar is practice measurements of crystal circuits, how to ensure the system is not vulnerable to process variant production. Now, if you have any questions during today's webinar, of course, feel free to ask them in the questions box and we'll be sure to answer them at the end. You can give us a shout out, let us know how you're feeling, even what projects you're working on. If you have something really neat that you would like to share with us, just let us know. Go ahead. I always have some of the answers coming in right now. Okay, we can't exactly help you with a time machine. I mean, if anybody's going to make a flux capacitor, it's going to be us. You know that. My only concern is I'm not entirely sure where you're going to find the plutonium. If your question doesn't get answered by the end of our segment, you can always email us at hereforyou@we-online.com or reach out to your local Würth Electronic representative. As a reminder, because you registered for today's webinar, you will automatically receive the recording and a PDF of the slides within the following 24 to 48 hours. Just look for an email from hereforyou@we-online.com. Again, if you have any questions, simply reply back to that email. And don't forget to register for our next webinar. It's coming up on August 26th, I believe. That's a Thursday. It is improving EMI performance of isolated power modules. Register online at www.we-online.com/webinars. And a huge shout out to our exclusive sponsor, DigiKey Electronics, for making all of our Würth Electronic webinars possible. I also want to mention that if you can't get enough of me, you can hear me every week on our new podcast, the Würth Electronic What's Up Radio podcast, available on Spotify, iTunes, Google Podcasts, all over the place, really. Again, that is the Würth Electronic What's Up Radio podcast, where I bring our application notes, our blogs, and our webinars to a strictly audio format. Now let's begin today's Würth Electronic webinar with Nick Amy presenting practice measurements of crystal circuits.
Okay, is that it, Amelia? I think I'm on, am I? Excellent. Thank you very much for the introduction. Let me see if I can remember how to share my screen while we do this. Okay, view and screen, 1 second. Wonderful, and now is the right time for the lorry outside to begin their shift. We'll just wait for him to go. Wonderful. Right, so thanks very much for joining us, guys. Practical measurements of crystal circuits, how to ensure systems are not vulnerable to process variation. That's the title. Your brief said something like, have you ever designed a crystal circuit which worked perfectly in your lab but brought yield issues when you went into mass production? Well, my brief behind this was that they said to me, Nick, it needs to be technical. They're a bunch of engineers. It's got to be geeky. So I'm trying to hit the right balance between having loads of formulas and stuff like that and having some lab work and that kind of stuff. So hopefully I hit the right balance. My objective today is to give you some tips on how to avoid a large scrap pile when you move into mass production. So let me begin with a story. Quite a few times in my career now, I've been working with customers that are doing really large volume stuff. So the guys that are doing consumer electronics, where the production volumes is sort of millions of pieces per quarter, And when you do those kind of volumes, obviously even a really low failure rate results in pallets and pallets of scrap material. And that's often manufactured for a subcontractor who's got some contract where they have to deal with that scrap material, and they get rather hot under the collar about it. And the problem that we have is that normally in that situation, you guys have done a pre-production run. You may even have made a few thousand pieces, and you found no problems at all when you were doing that. So something's happened when you moved into really large volume production. What the subcontractors have said is that they take the crystal off, they swap it for a new crystal, the fault goes away, so therefore it must be the crystal that's at fault. So it must be my problem, yeah? But the problem is that when they send the crystal back to me and I do some tests, I find that the crystal is perfectly fine. It's within the specification that you asked for. So this is the situation that we're trying to avoid, really, isn't it? What's the solution? Well, what we've done when this has happened is we've done some measurements on the PCB. We've taken a PCB from the customer, and what we found is that although it's okay, but everything is quite close to the limit, and that means that sometimes when you move into those really large volumes, you get the worst case of all the combination of the components that are on that PCB, and that's what's resulting in the failure. And the good news is that there's a few minor changes you can make, and then the fault goes away. Yeah, so no more scrap material. So today, what I'm going to talk about is how I made those measurements and the theory behind those measurements, and then how you can apply that to your own work in your own lab and try and avoid being in that situation in the first place. Okay, what I'm not going to talk about today is the basics on how crystals are manufactured or how you specify them and that kind of stuff. If you do want that kind of info, find loads of stuff on our website. There's some really great webinars that my colleagues have done like this in the past, and there's some links there if you want to look those up. Yeah. Okay, quick note on the PCB that I'm going to be discussing. So I'm going to focus on one PCB, talk you through these measurements and how we did it. Obviously, I can't talk about one of my customers' PCBs and what went wrong and how bad their failure rate was, because that's not really what people like to talk about. So instead, I've had to choose a PCB that we use. This is a PCB we use in our laboratory. It's part of our product approval process. So we use this PCB when we want to do things like board flex, termination strength, that kind of stuff. It's just a really basic circuit. You can put a crystal on it. It runs it in an oscillator, and you put stresses onto the crystal if you need to, yeah? So this is the raw circuit that we're running on this PCB. It's a crystal oscillator driver from Texas Instruments. It's a pretty basic Pierce oscillator design. So you can see X1 there is the amplifier, and there's a feedback loop with a crystal in it. And then there's a few more buffers there that are isolating what's happening in the feedback loop from whatever you guys do on the outside world, yeah? And here we can see our version of that drawn up on our Eagle PC before we had it manufactured, yeah? So what have we got here? So this is the amplifier circuit, X1 and X2, and we're coming out from the amplifier here. We're going through this R2 here, which is the feedback loop, and that forces that buffer to be an amplifier. We've got R1 over here, which is the current limiter for the circuit, so it just limits how much current is going around the crystal feedback loop there. And C2 and C5, which are two 22 picofarad, go down and form the total, the load capacitance of the circuit, and that needs to match the load capacitance that's on the data sheet for the crystal. And for this particular job, what I'm going to talk about is one specific crystal, and it's a 26 megahertz crystal in a 2.5 by 2 millimeter package. We call that a CFPX 218, but it's nothing special. Bog standard crystal from stores. This particular one has got a 20 ppm tolerance when it's at room temperature, further 20 ppm over -40 to 85. It's supposed to run with a 10 picofarad capacitive load. Okay, so that's what we're going to be talking about today and looking at, yeah? Now then, hold on a minute. Apparently I'm not sharing anymore. What's going on there? I'm assuming you guys can see me. Amelia, if there's a problem, let me know, yeah? Okay.
Yeah, Nick, you're okay. We were just hearing some background noise, so we went ahead and shut your camera off.
Ah, brilliant. Okay, I can pick my nose again then. Right. I'm assuming you can see my screen now, yeah?
Yes.
Great. Okay, so if I finish all of this presentation really quickly, what I can tell you is that after we did all those tests, looking at the viability of this circuit, what we found is that we want to change from 22 picofarads to 15 picofarads for these two, and that we want to change R1 from a 1 kilo ohm to a 4K7, yeah? So that could be considered the end of this presentation, but of course what you guys want to know is, why do those need to change? How did I make the measurements? And is it something that you could do yourself? Yeah. So let's take a look at how we do the measurements. The first measurement we're going to make is we're going to measure the frequency on the PCB. Yeah. Pretty obvious why we need to do that. The component that we're discussing is a crystal. It's designed to make a frequency. It runs on your PCB, so we better find out how it's running. We better measure that frequency when it's on the PCB. Yeah. Some considerations you need to think about if you're going to do this type of measurement. If you put any kind of capacitance into that feedback loop of the crystal, that capacitor frequency to a different frequency. So you will not be looking at what it was before you, yeah? So you need to avoid adding capacitance to the feedback loop. In an ideal situation, what you want to do is you want to find an alternative point on the PCB where you can measure the frequency, where it's a buffered output, yeah? When I was a kid and we were microprocessors, they used to have a clock output pin. That was fantastic for doing this with. Nowadays, I have hardly ever seen that anymore. It's normally used as an I/O pin or something. You might have some software functionality that allows you to make one of your I/O pins into a clock output pin. If you do, fantastic. If you were asking me to do that work, I wouldn't have a clue how to program your system, and I wouldn't want to touch your firmware. So for me, what I'm going to do is I use this FET. This one's from Tektronix. It's a P645. It's a really cool probe for doing this with because it's got less than 1 picofarads on the input capacitance. And actually, I've been playing with this probe a while, and I can tell you it's about 0.4 picofarads on the input capacitance there. So when I put that in the middle of the feedback loop on the side of the crystal, it doesn't change the frequency by a great deal. Okay, so here we are. We're going to do our first measurement, and there you can see at the top there, we've got our probe. And what I'm doing is I'm pushing the probe onto the active pin of the crystal there. And on the oscilloscope up here, you can see the purple line. That's the frequency coming directly from that probe. So you can see how I'm measuring the frequency. On this instrument, I then take that to a signal output and feed that back into a frequency counter, and I can get the frequency from there. Yeah, pretty easy. Okay, but this crystal, this PCB was the one that we made in order that we could measure the frequency without having to do that. So I'm really lucky because I can get the signal. And that's what our green trace is on the top there. We've got a square wave coming directly from that, which is lucky because that's what I made it for. As I said, I'm yet to see a customer's PCB that's got that function. If you did have a function on your PCB that gave you a frequency output, it was some mathematical derivative, maybe a multiple or a division, it'd be perfectly fine to use that, yeah? The only thing you need to be cautious of is
for interruption here. Can you hear me?
I can, Amelia. How you doing?
Well, pretty good, but it seems like we're getting quite a bit of feedback from your microphone. Is there any way that you could switch your microphones?
I have got another microphone because I had a feeling this might happen. Let me just disconnect from, how's that, Amelia? Am I coming through?
Yes, you're coming through very well. Thank you. We do
Excellent.
have a
Right.
request. Would you mind repeating the measurement details of this slide?
The measurement details of this slide. So is that what the measurements are? Yep. Okay, let me start this slide all over again. Sorry about that interruption, guys. Okay,
Thank you very much.
so what we're trying to do is we're trying to measure the frequency that's coming from the crystal oscillator circuit while it's live and running on your PCB. Yeah, I'm using a FET probe because a FET probe has got a very low input capacitance, and I'm pushing the FET probe onto the side of the crystal on the active circuit, and then my output is coming from that FET probe up to the oscilloscope, and you can see the purple line there, the purple trace. This is a TDS 5104 oscilloscope, which I'm a big fan of because it's got a signal out on the back channel. So whatever's coming in on the input is then buffered and repeated on the output, and that allows me to connect it directly up to this frequency counter over here. Yeah. Just for giggles, because I can on this PCB, I'm also taking the RF output and putting that onto a different channel on the scope, and that's the green trace that you can see up here. Yeah. And so I've got that on the other counter here. I can do that on my PCB, as I said, because my PCB is designed in order to give me that RF output so I can measure the frequency of a crystal. You probably won't be able to do that on your PCB because probably your microprocessor doesn't have that function. And what I was just discussing was the idea that if you had some function that gave you a division of the frequency or a multiple of the frequency, then it's perfectly fine to use that as long as you follow the math through and work in parts per million rather than hertz. One thing you do need to be careful of is if there's any sort of phase lock loop or any sort of compensation network running on that, then you can't use that because then you'll start seeing the frequency deviations that are given by those phase lock loops. Yeah, so you've got to make sure that you've got a pure derivative of the crystal frequency. Okay, quick note here. I'm trying to weave in as many notes as I can from what I've learned over the years. Yeah, the earth connection that you're going to use here, if you look at your microprocessor, you'll notice you've got a crystal in, a crystal out, and a ground plane, and that's be right next door to it. That'll be an analog ground plane, and there'll be some sort of isolation from the rest of the ground, just so that the analog circuit doesn't get the digital switching noise from the rest of your system. Yeah. I would recommend that if you're doing this kind of probing, that you use that analog ground as the ground for your probe. You'll find that you just got less noise on your signal. Yeah. And another one that sounds really silly is when you are mucking about with crystal oscillators and looking at the PCB, do remember to remove the flux and allow the crystal to cool before you make a measurement. I learned the hard way on the flux thing. I forgot once to take the flux off. And I don't know if you're aware of this, but flux has got a resistance that's in the order of a few 100,000 ohms, and it changes really dramatically from the moisture on your breath or the temperature or the flexure on the board. And so you get really wild readings if that happens to form part of the feedback loop, if that flux is across that. Like I say, I spent a day swearing at a board because it kept measuring different things every time I looked at it until I realized, oh, I didn't clean the flux off properly. So let me save you that day. Okay, but I think the question was, what are the measurements from this? So here are the actual measurements that we got. So this crystal was supposed to be a 26 megahertz crystal, and the frequency that we're actually getting from the PCB here is minus 578 hertz, which if you divide that by 26 gives you minus 22 parts per million. Yeah. So that's our first measurement. That's our baseline measurement for what's happening on the PCB before we start looking at anything in any detail. Okay, the next measurement we're going to make is we're going to remove the crystal from the PCB and we're going to measure the crystal in the lab under ideal conditions. And so how are we going to do that? What I'm going to use is this equipment that's called the Saunders 250B. There are other guys that do similar equipment. It's actually a network analyzer on a card. So it broadcasts a frequency from one channel. We put that across the test fixture here. The crystal sits in the test fixture and the cable returns that back to the network analyzer, and it measures the phase and gain of the signal as compared to what it broadcasts to what it reads back. Yeah. The really cool thing about an instrument like this is that it does conform to BS 60444 Part 1, measurement of quartz crystal unit parameters by zero phase technique, and anyone in my industry will be able to quote that to you. That is the de facto international standard for how you measure a piece of quartz. We need to have that because a quartz is basically a lump of rock. It doesn't do anything unless you excite it. So you need to have an agreed method for how you excite it and how you measure it. Yeah. It's a pretty cool instrument. It'll give you a reading in less than a second, and those readings will be accurate to less than 1 part per million. And mostly what I really love about it is it gives me those measurements in parameters that are crystal parameters rather than network analyzer parameters. And we'll go into that in a few detail on the next couple of slides. Okay, how are we going to do this measurement? Pretty straightforward. We're just going to desolder the crystal from the PCB. We're going to wait for it to cool down, and then we're going to make the measurement. What I've said here, officially I'm supposed to say 24 hours to let it de-stress and cool down before you make the measurement. In truth, probably if it's a small crystal and you weren't too heavy with a soldering iron, you probably need to wait maybe 40 minutes, an hour for it to settle down. If you are making the measurements, what you'll notice is that the frequency keeps changing, and when it stops changing, it's probably because it's finished cooling down, and that's probably accurate enough for what you need. Temperature is really important for crystals. Crystals do change frequency over temperature, so in our lab, everything is 25 degrees. In your lab, you need to make sure you've got somewhere close to 25 and that it's an even temperature. Yeah. Okay, so let's go ahead and use that instrument. So what we've got here is that instrument on the bench. The card is sat in the back of the PC. The cables are coming down onto the test fixture. I've got a green PCB and I've got a box full of those for all the different crystal sizes that we do. And over here, you can see the software output. So it's telling me the measurements of the crystal that's underneath that little white arm there. And here we are with the actual measurements. So I'm going to talk you through these, and then the next slide, I'll try and give you some meaning for these. I'm hoping to try and make it all a little less cloudy if you don't work with these numbers all the time. So the first measurement is FR, and we can see here that's minus 100 parts per million. Yeah, that's as reference to 26 megahertz because that's our frequency for the crystal. And FR means the resonant frequency of the crystal. So that is the crystal's natural resonant frequency. Yeah. The next measurement we've got is FL, and FL means the frequency when it's running with the correct capacitive load. And you'll remember that our crystal has got a 10 picofarad capacitive load, and you can see here in the instrument setup, I've told it that that's what we want, and it's telling me that under that condition, the frequency is minus 2 parts per million away from 26 megahertz. So not too far off. Okay, the next 4 measurements, C0, C1, RL, and L1 are what we call the crystal equivalent circuit, which I've put up here for you. So this circuit, in this configuration, C0 represents the holder capacitance. So crystals are lumps of rock and they have a body around them to encapsulate them. That body has some capacitance value, and C0 represents that value in the circuit. And then the R, C, and L combine to form what we call the motional arm, because quartz crystals physically vibrate. So we call it motion because there's physical motion going on there. Yeah. And in theory, if you put capacitors and inductors and resistors together of these values in that circuit, you would have a circuit that had the same resonant frequency. So that's the same FR value as this particular crystal has. Because what you'd find is you'd have a terrible Q value compared to the crystal. And so it would be really quite difficult to maintain. Yeah. But the last value we've got here is a really interesting figure. This is what we call the trim sensitivity. And this is a measure of how much the frequency will change if the load capacitance was 1 picofarad away from what it should be. So our load capacitance should be 10 picofarads. What we're saying is that if our load capacitance were 9 picofarads or 11 picofarads, that would change the frequency by 9.4. So that would mean that our FL value here, because this is the one with the load taken into account, would then go from minus 2.1, we'd add 9.4, and we'd be at minus 11.5. So this is quite an important value because it tells us how accurately we need to get the capacitive load on the circuit. Okay. And more importantly, we've now got a set of measurements we can use in the rest of our technique to look at how the crystal behaves. Yeah. So I think that if you don't work in my industry and you don't look at crystals every day, perhaps those numbers are a little bit alien for you. And I tried to think of how they might be, how I could try and give you some visual representation of what they mean. So here I'm using the same instrument and I'm using it in a more conventional network analyzer setup. So we've got a sweep on the x-axis here that goes about 26 megahertz. So we're going from just below to just above 26 megahertz. That's our crystal resonant frequency. And the green line represents the losses, or as seen between what's broadcast from the network analyzer and what comes back. And what you can see is that there's a point here where the losses are the least. Yeah. And that is, in fact, our FR measurement that we saw first. So that's our minus 101 parts per million away. And you can see that's a minus value because it's just below 26 megahertz, yeah? And on the other side here, on the slope coming down, you can see I've put a marker exactly where our minus 2.1 FL value is here. And so I'm trying to help you understand where that is. Again, it's just below the 26 megahertz line because it's only 2 parts per million below. And our trim value that we just talked about, yeah, that is actually proportional to the slope that's on that graph at that point, yeah. The other thing that's interesting to note here is you've got the phase marked out in the blue, and the phase shift is about 180 degrees phase shift at the frequencies that are between these 2 points. So our oscillator circuit that we're using is called a Pierce oscillator circuit. It relies on an inverting buffer, and the crystal has to have a 180 degree phase shift itself. They combine to make 380 degree phase, and that's how we get our amplifier through. And that has quite a neat effect because it makes it much harder for frequencies that are outside of this range to be amplified. Yeah. So I hope that slide puts some relevance to the numbers that we were looking at in the previous slide. That was my intention with this one. Okay, but the really important thing is if you were able to pay attention, then the frequency that we measured when we were on the PCB was minus 22 parts per million, and the frequency off the PCB of the crystal on its own is minus 2 parts per million. So we got a 20 ppm shift in frequency happening, and we need to understand why that's happening. Yeah. So I apologize for this slide. It's going to end up with a lot of numbers. I really should find a better way to do it, but today is too late. So here we go. We have a requirement to make 26 megahertz, and the PCB is, and the crystal is specified to have 10 picofarad load. Our circuit here takes advantage of 22 picofarads, which if you combine those together to make the CL value using this formula, it comes out at about 11 picofarads. And that's not far away from 10 picofarads, is it? So it should be okay, yeah? No. The first thing you need to take into account is that that's not the whole story, because there is also a lot of stray capacitance on your PCB. So PCBs themselves have got stray capacitance. The copper tracks obviously form capacitance between the different layers. And also the IC has got capacitance on the input here. And so the combination of all of those need to be taken into account when you work out what value capacitors you're going to use here. Okay, here we go. So originally, we made our measurement using two 22 picofarad capacitors, and we said it was minus 22 parts per million. And the thing is, we didn't ever want that to be 26 megahertz dead on. First thing you need to recognize is that you're trying to make that the same as the frequency that it is when you measure the crystal in isolation. So we need to go to minus 2 parts per million. Yeah, you don't want an offset between what the crystal is and what's happening on your PCB. The problem is the stray capacitance, and because we've calculated the trim value in our measurements, so we know how many ppm the crystal is going to shift if the capacitance is wrong, and so we can do a bit of maths and we can calculate what the total is that you're seeing on the PCB, and it turns out it's about 13.8 picofarads. Yeah, So it's a little bit higher than the 10 picofarads, and it's even higher than our 11 picofarads. And now we can see we've got a stray capacitance of 2.8 picofarads. Yeah, and that's what's causing our problem. So we can do some more maths, or you can just get some capacitors and change them, whichever you find quickest. And eventually we find that if we change from 22 picofarads to 15 picofarads in this instance, then we end up with a frequency offset of minus 0.4 parts per million when we're on the PCB. Yeah. So we've made a massive improvement in the accuracy of the frequency. And what we found is that now we've taken into account this 2.8 picofarads that stray on the PCB to give us a total capacitance of 10.3. Yeah. So we're a lot closer to the 10 ppm that the crystal specification is expecting. So just to reiterate, we started with 222 picofarads, which including the stray gave us 13.8 picofarads. We've swapped that now, and we're using 215 picofarads, and that gives us a combined with the stray capacitance of 10.2 picofarads on the PCB. Okay, that's really important because now the frequency variation when we go into production will match the frequency variation that we're seeing on the crystal. So in other words, as long as the crystals are all within the specification that you asked for, so is the frequency on your PCB. If you have an offset, then you'll have a window where some of the crystals are in spec when they're on your PCB and some of them won't be in spec because you've got the wrong load capacitance there, yeah? So that's the first correction that we've made to this PCB. And again, I apologize for the number of numbers on that slide. I promise the rest don't have so many. Okay, so let's talk a little bit more detail about stray capacitance here. Yeah. So stray capacitance includes the PCB stray capacitance and the IC stray capacitance. As a rule of thumb, when you're doing your maths, it's normally between 2 picofarads or 5 picofarads, depending on your PCB layout, how small your components are, how tight you've got everything, yeah? And in the graph on the right, what I've showed is two crystals, both normalized to run with 30 picofarads. So you can see the frequency deviation is normalized to 0 at 30 picofarads load, yeah? The black line represents a really big crystal. It's the biggest crystal that we sell at the moment. And the red line here represents a smaller crystal, a 3.2 by 2.5 crystal, yeah? And so what we're plotting here is how much the frequency changes if the load capacitance is moved away from what it should be, yeah? And what I want you to take away from this is that the larger crystal here, the frequency deviation for the same change in load, the frequency deviation is much, much bigger. So this effect of trim capacitance is much worse on big crystals, yeah? And the other thing that I want you to take away from this is that if I were to change from 30 picofarads to 25 picofarads, the graph for both crystals is relatively shallow change in frequency. But if I change from 15 to 10 picofarads, you can see that the chart is starting to show a much steeper gradient here. So in other words, when you run a circuit with a low capacitive load, then that issue about the trim capacitance becomes a much bigger problem than when you ran with a much bigger load, yeah? So just to reiterate, lower CL will give you a higher trim, and a larger CL a larger crystal will also give you a higher trim. And finally, this effect isn't a linear effect. You can see that this is not a linear thing. These are exponential decay graphs, so it can get really serious, yeah? Obvious question, how serious can this problem get? So I popped into my lab as I was putting this presentation together and pulled off the first 4 or 5 sets of results from various crystals that we manufacture and just put them together like this. And you can see values quite often in the order of 20 parts per million. That's 20 parts per million change in frequency for a 1 picofarad change in load. And obviously, I'm going to draw your attention to this one because this guy is going to be 60 parts per million out of frequency if you're 1 picofarad out with your load. So I think this guy really emphasizes how it's very important to consider if you need accurate frequency, you need to get that load capacitance to be accurate on your PCB. Yeah. Okay. Well done, guys. If you're still with me, that was some pretty in-depth crystal stuff and maths there. But we're going to move on to a different measurement now. Having done that one and made those corrections, this next measurement is called current dissipation and drive level. Okay. Why are we looking at current dissipation and drive level? Because on the data sheet for this crystal, it states that the drive level should be less than 100 microwatts. Yeah, and that too much drive level will give you an incorrect frequency and it might even damage your crystal. Some considerations when we try and make this measurement. Yeah, we're trying to measure the current draw through the crystal at this stage. If my probing and measurement technique affect the actual frequency by a few hertz, I don't care anymore. That's not my priority anymore. I just want to not affect how much current is being put through the crystal. How am I going to do that myself? Again, I'm really lucky. I've got some cool toys in my lab. I've got this current probe, again, a Tektronix Chubb. It's really nice. It's very accurate, and it's got a 1-to-1 current ratio, which means the voltage level on the oscilloscope is proportional to the current that's being passed through the circuit. Yeah, that's because I'm not very good at maths and I really like that. So here we are, we're on the PCB and this is how we're going to physically do this measurement. It's a bit more complex than the previous one. We've got to desolder the crystal from the PCB and then I'm going to solder the crystal with 2 pads connected and 2 pads up in the air. Tombstoning, I think it's called. Yeah. And I'm going to connect a piece of wire from the other active pad on the crystal, pass it through my probe and down onto the active pad on the PCB to complete the circuit. Yeah. And now when I power the circuit up, I can see the oscillation being read through the current probe. And again, it's the purple trace on the oscilloscope here. And here the peak-to-peak voltage is proportional to the peak-to-peak current that's passing through that crystal. The green trace, of course, is the RF trace that I had before from this thing, just confirming that I'm looking at the right frequency. Okay, so if you want to know the current draw or the current dissipation or the drive level of the crystal, what you're going to need to do is take the peak-to-peak voltage you've got here. You're going to need to divide that by 2 to make it a peak voltage, multiply it by 0.707 in order to get an RMS current level. And then you can use our Ohm's law that we've all known since we were at school. In order to do that, you're going to use the current that you've just calculated based on the measurement you've just done. And then you're going to use the resistance, which is the RL value that we got when we looked at the crystal in isolation using that network analyzer equipment. Yeah. So I did that to this PCB. And what I found was that I had 9.6 millivolts peak to peak, which gave me 3.4 volts RMS, which is a 1-to-1 ratio, so it's 3.4 milliamps. And then I used the RL, which was 24.3 ohms, and that combines to give me a power dissipation in the crystal at the moment of about 280 microwatts. And our data sheet said not more than 100 microwatts. So I got a problem. We got too much current being dissipated in that crystal. Okay, so what am I going to do about that? So that's just the same numbers we had before. And what I'm going to do, let's have a look at our circuit again. We've got on this circuit, we've got R1 here, which is a current limiter. So our feedback loop is coming from the output of the amplifier through pin 4, through R1, over the crystal and back to the input. So if I increase the value of R1, I'm going to decrease the current flow through that. And so I'll decrease the power dissipated in the crystal. And by mucking about with a few values, I was able to experiment and find that if I change that to 4K7 as a value for R1, then the maths plays out and I end up with 64 microwatts being dissipated in the crystal, which is nicely below my 100 microwatts on my data sheet. So everything's looking good again. Yeah. So that's our second correction that we've made to this PCB that's just given us, we're nicely inside all the safety margins you might like. Okay. Why is it significant? What's the problem if I put too much drive through a crystal? Okay,
So the data sheet says the maximum drive level. That is an absolute maximum value. Above that, you're risking doing damage to the crystal, okay? If I overdrive a crystal by a small amount, then vibrations on the crystal don't dissipate before they reach the edge of the blank. And so I'll get reflection waves causing spurious frequencies. So I've got 3 crystals pictured here. I've opened the lid and you can see a piece of quartz with an electrode plated on either side. So let's start with this one on the left because it's a nice, easy one to explain. Here you can see it's a very old crystal, but you can see a round disc of quartz. You can see a silver electrode plated on one side, connected out to this mounting structure on the right. And on the left-hand side, you can see through the crystal that there is in fact an electrode plated on the other side. So the active area of the quartz, the piece that's doing the electronics, is directly beneath those 2 electrodes. That's the area where the electricity signal is passing, and so that's where the vibration is happening within the lump of rock. Yeah, vibrations. I like to explain it. If you can consider that you had a still pond and you threw a rock in the center of the pond, you would have vibrations coming from the point of excitation where the rock hit the water. Those vibrations will dissipate in energy as they move out through the surface of the water, and so it's the same in the quartz crystal. What you're looking for is for that energy from that vibration to have completely dissipated before it gets to the edge of the quartz. If it doesn't, you'll get a reflection wave coming back from there, and that reflection wave will come back inwards, and that will start to have an interplay with the waves that are already there, and there's a risk that that interplay will result in a spurious frequency, some unwanted frequency existing on your feedback loop. And it's possible that you'll then see that coming on the output from your oscillator. Yeah. So on the other hand, if we really massively overdrive a crystal, yeah, then the physical vibrations that will be happening will be coming right out to the edge here, and they may even start to vibrate the mounting structure. So now if I turn to this picture on the right here, this is the same crystal type as what we're using for the discussion on this PCB. You can see a crystal here, that's the clear square piece of quartz, the electrode, and you can see the mounting structure here. So if the vibrations that are supposed to be contained underneath this plate and allowed to dissipate before they reach the edge of this, if they were, they may even start to vibrate so much that they start to rip apart this mounting structure. And if that happens, the first thing that you would observe is that the resistance value of the crystal would begin to go up. And finally, I have once in my life seen a crystal where that mounting structure was completely fractured, but they're so close together that it was actually acting as a capacitor that was in series with the crystal. And I only found that out through some X-ray analysis and stuff like that, but that's what the risk is. So if you put too much drive level through a crystal, that's what you're looking at the problems being, yeah. However, all you need to do, you don't need to be too worried about this. You just need to get the drive level below the maximum that's on the data sheet, yeah. If you look at crystal data sheets from any of us that do crystals, what you'll notice is that the drive level is a uniform value that we stick on all of our crystals. We don't change it depending on the frequency or depending on the specification or anything like that, yeah? So that tells you that it's a pretty, there's a pretty broad safety margin even in our own work when we do that, yeah? So don't be too panicky about, you know, oh, I'm 5 microwatts just over the drive level. Oh, I need to get that down. Honestly, I would probably say that's going to be fine, yeah? Final note on this subject. If you look on some data sheets, you'll see a value that says the typical drive level. That's got nothing to do with this conversation. That is actually just a reflection for all of the other measurements that you've made on that data sheet. And it's just saying that those measurements are made with reference to that typical drive level. Yeah. Okay. So we've done frequency accuracy, we've done current dissipation. The final measurement that we're going to do here is called gain margin, yeah? So new measurement type. Why are we doing the gain margin? It's quite an important one, this one, in order for a circuit to oscillate, then the gain of the amplifier must be larger than the impedance of the loop. Yeah. So the amplifier amplifies the signal, and the crystal network loop has got losses in it. So what's coming on the output from the amplifier is fed back through the crystal and back to the input. Obviously, if the losses that are seen here are greater than the amplification here, then it won't get going. It won't amplify and it won't oscillate. Yeah. How are we going to make an assessment of that? How are we going to make a measurement of that phenomenon? Yeah. Well, what we're going to do is we're going to look to find a ratio of the gain of the amplifier versus the losses of the loop. And in order to do that, we need both numbers to be in the same units. So we're going to need to have a negative resistance value for the amplifier gain. So that's an ohmic value. Because it's a gain, it's going to be a negative ohmic value. And the impedance of the loop is the crystal R value, the resistance value that we measured when we measured the crystal off the circuit. Yeah. And if we divide one by the other, then we get a negative resistance ratio. Yeah. And now I've got it in a number. Now I can tell you that if that number is greater than 1, then the circuit will oscillate. But the problem is, yeah, but what if the resistance of this crystal is a little bit more than the previous one? What if the amplifier gain is a little bit less than the previous one? What happens when I heat these things up or whatever, yeah? So actually what I'm going to tell you is that you need that negative resistance ratio should be a greater value than 3. Now you've got a bit of safety margin in there. Now you feel a bit more confident that you're not going to have, like we talked about before, some small percentage of components that combine in a way where you've got less amplification and you've got higher resistance to the crystal and it just doesn't quite have enough to get going, yeah? Well, actually, I'm going to tell you that I really want that value to be 5. When I make those measurements on other people's PCBs, if I see the values greater than 5, I think, yeah, that's great. I feel really confident. If I see the values greater than 3, I might tell you that you probably want to have a little look at that. You might be able to eke a bit more and push it up to 5, and that will be safer, yeah? But if it's greater than 5, everything's great. So considerations when we try and look at this kind of stuff. So small crystals have got a higher resistance, so the negative resistance ratio will be less. That's quite relevant in today's world as everybody is now trying to get components smaller and smaller and smaller. And so if you did this kind of work a few years ago with a crystal of one particular size, you can't just take those values and reassess, reuse them in a modern circuit. If you change to a smaller crystal, you're going to need to look at this again. Yeah. How am I going to do this in the lab? Well, it's pretty easy, to be honest. I'm going to take the crystal off and I'm going to add a series resistor in circuit with it, and I'm going to keep doing that with bigger resistor values until it stops oscillating. So here we go. Here's a picture of how I'm going to do that measurement. And again, what I've done is I've tombstoned the crystal here. So he's stood upright, and I've got a resistor in series with the crystal to complete the circuit. And I'm going to power the thing up after it's cooled down and I've cleaned it all off. And yep, you can tell me that I didn't clean this PCB very well. Actually, that's flux off residue, and this camera just seems to have caught the light on it particularly badly on that photo. So what I'm going to do is I'm going to power the circuit and I'm going to make sure it starts. Yeah, startup here is much more important than continued oscillation, which is one reason why I don't recommend using a pot in this circuit. Some people will tell you that you can do this with a pot and you just wind the value of the pot up until it stops. I don't think that's very safe, because at the point when you very first start a crystal oscillator circuit, what's happening is that the amplifier begins by amplifying white noise, Johnson noise, thermal noise that's in the system, and then the crystal acts as a filter, blocks all of those frequencies apart from its resonant frequency. Yeah, so that's a really sensitive moment when that oscillation is getting going. It's the hardest part for a crystal circuit to work. Yeah, so by always looking at the startup, you're always looking at the worst case, the most flaky part of the measurement. Yeah. Another reason why I don't recommend using a pot myself is because pots have got capacitive and inductive elements inside them because of the way they're manufactured and designed. And they've also got a really nasty hysteresis effect. So, you know, if you turn it one way and it's one value and you turn it quarter of a turn the other way and it doesn't start to change for a bit, I just find it's a lot cleaner if you just put fixed resistors onto the PCB like this and keep going with higher and higher values until you switch the circuit on and nothing happens, and then go back to a value a little bit lower, and that's the value you're looking for. So here's the actual measurements that I made on the PCB that we've been looking at. So what I found is I can get 4,500 ohms in series with that crystal, and it's still just about starting up. Anything higher than that, and it doesn't start up anymore. Yeah. I've got a measured RL value earlier on that we had for this crystal, which was 43 ohms, but that's not the RL value that I'm going to use. I'm going to use the maximum resistance value from the data sheet, which for this crystal is actually 100 ohms. So I'm going to take 4,500, divide it by 100, and I've got a negative resistance ratio of 45, which is well over the 5 that I was looking for. So I'm really happy about that. Yeah. That's not surprising because I'm a crystal oscillator guy and I've designed the circuit to drive a crystal oscillator. I wasn't designing the circuit to minimize the current draw, and I wasn't doing anything funny like that. So it's quite high value. In reality, your PCB will be probably a bit lower than that, yeah. But there we go. So we did a measurement and we got a thumbs up for that one. Okay, gain margin. Let's talk again about why I used the resistance that was on the data sheet, the maximum resistance, rather than the resistance that I measured on the crystal, yeah? So for that specific crystal that I'm using for this presentation, I just popped in the lab again and pulled off some results, and I happen to have some results that show 125 samples of that part number being measured, and this is the distribution of the resistance, yeah? And you can see that it's a sort of Gaussian distribution with a mean value. And in fact, my value of 24 was quite high. The mean value, I may have ended up using a crystal that had a value of 15 ohms or something like that, because that's my mean here, yeah? But what you can see worst is that I got this one part in 125 that's got a 40 ohm resistance. So if I used 24 ohms to do my maths, and I had been marginal, I might not have been able to start up with this 40 ohm part, yeah? So if I tried to calculate my negative resistance using 45,000 ohms as the value that it just about starts up at, divide it by the actual resistance of the crystal, I'd have a negative resistance ratio of 185, which looks great. If I'd use the worst case in the batch, it would be 117, this 38 ohms over here. And if I use the datasheet value, I get 45, yeah? So I'm just trying to show you how much your value can change. Bearing in mind, my PCB is designed to really drive the crystal nicely. Yours will be, these values will be much lower, so that you can see the spread of values there is really significant, yeah? So it's important that you use the worst case resistance value you're ever going to see. That's why we take the one off the data sheet. Otherwise, and I've had this one, this guy can be the cause of your failure rate when you move into mass production. This outlier in the group, if you were using the mean value, you may find that it doesn't work on a few crystals, yeah? Okay, so that would leave you to wonder what on earth would you do if the gain margin was too small. If our negative resistance ratio was less than 5 or less than 3, what are we going to do about it? Okay, first thing you could try is, I want to tell you, you could use a bigger crystal. And here's 3 crystals. The middle one is the size for the crystal that we're using, and so the maximum resistance for this crystal at 26 megahertz is 100 ohms. If I used a crystal that was smaller than that, and this one's a quarter of that size, then you can see the maximum resistance value is going to be double. So that would affect our gain margin quite dramatically. And you can see if I went back to that really big crystal that we do, then the resistance value is going to be much, much less. So if I use a bigger crystal, I get a much better gain margin, yeah? And you're all screaming at me that I can't do that because I've done my PCB layout and I can't just put a bigger component on there now. Fair enough. So alternatives, you can try and lower the value of R1. Again, R1 is the control for how much current is being allowed to flow through this loop. So therefore, it also affects the losses in that loop. If I put a lower value, then I'm going to increase the gain margin. Yeah. Trouble is, of course, that affects the drive level, and as we saw in this particular circuit, was a bit difficult. So you may have to play around with the ratios and see if you can get a ratio where your drive level is below the spec and your gain margin is above what you need it to be. Yeah. Well, there is a third method. Yeah. The third method is you can change to use a crystal with a lower CL value. So we're using a 10 picofarad CL value. I can use a crystal with a lower CL value, and what that will do is it will lower the losses in the loop. So obviously, if I use a lower CL value on the crystal, I'm going to change these capacitors to be a lower value. And what that means is that the losses within that loop are going to be a lot less. Yeah. The downside of doing that is that the trim value is going to go up. You remember the trim value we talked about in that graph where I showed you if you use a lower CL, then you have a higher trim value. So that means that you're going to need to be really, really accurate with your capacitor values and your stray PCB calculation. Otherwise, you're going to be running off frequency. Yeah. Now, the final point there, talking about how using lower capacitors gives you less losses in that loop. I'll be honest with you, when I first came across that a few years ago, I found that a little bit of a difficult concept to understand. So let me try and explain that in a bit more detail. The capacitors here are a leakage to ground. This is an RF circuit. It's running at around 26 megahertz. So if I look at the capacitor's reactance formula, it's 1/2 pi FC, F being our 26 megahertz, C being the value of the capacitor. And if I do some calculations, you can see that our 22 picofarad capacitors that we were using here, they actually have a reactance value of 278 kiloohms. So what that means is at 26 megahertz, they represent a 286 kiloohm resistor down to ground. So that's some loss in our feedback loop that's happening there. Yeah. And you can see I've just calculated the reactance value for a few different capacitors, plotted them on the graph here so that you can illustrate the fact that if you use a lower capacitance, then the reactance goes up. So therefore the losses down to ground are less. Yeah. And if you're still struggling to understand that, because it took me quite a few attempts to get that clear in my head, one of my colleagues did a webinar where she talked in great detail about this type of stuff, and she explains it again. So do feel free to have a look at her webinar and see if that makes it more clear for you. Yeah. Okay, well done, guys. That's been a pretty intense hour. We've done some measurements, we've done some maths, and hopefully we've made some improvements on a PCB. Yeah. So just to recap where we were at the beginning, what we did is we changed our two capacitors from 22 picofarads to 15 picofarads, and we changed from 1 kiloohm here to 4 kiloohm, 4K7 here. And we said, but why have we done that? Well, I hope now that you can see that what we were doing was we were decreasing the drive level so that we could bring the drive level through the crystal to be within specification, and we were increasing the frequency accuracy by increasing the accuracy of the CL value, the capacitive load on your PCB. Yeah. How did we make those measurements? Well, we had a bit of fun in the lab. We used some tools, we used some probes. It was good fun. And yep, I promised you that I would show you how you can do that at home. So you're quite right. Some of the instruments and some of the probes that I've got are quite expensive and they're quite specialist to crystals. So I spent a bit of time thinking, how would I do that if I didn't work in a lab that specialized in measuring crystals? So here we go. Here's some attempts. Yeah. The first measurement that we tried to make was the frequency measurement when it was on your PCB. Yeah. And I used that FET probe, and that FET probe is really expensive. So me and my colleagues, we kind of scratched our head and wondered about different techniques. We tried a few different things, and in the end, what I found is that I had an EMI sniffer probe, and I connected that to a spectrum analyzer, and I put the sniffer probe near the crystal, and I can make a frequency measurement using that. I can pick up on the frequency from the circuit, yeah? And this sniffer probe, by the way, was really, really cheap. I made it out of a pen and a few bits of mod wire and a bit of heat shrink and an RF connector, yeah? And there it is, assembled, and there's my network analyzer, my spectrum analyzer with a peak on it, and here's my probe sitting on top of the crystal. Well, crucially, it's not actually right on top of the crystal because crystals have got a metal lid, and the metal lid is connected to ground, so that's an EMI shield, yeah? Where I put this is on the PCB track just between the crystal and the capacitor, and that was where I got the loudest signal on this probe, yeah? So there's a method for measuring frequency, although I must admit that maybe my life is a bit easier because this PCB is only creating one frequency. Your PCB will no doubt have lots of digital switching noise. You'll have address buses and data buses firing off all over the place. But nonetheless, I hope that gives you an insight into a different method to make that measurement. And yeah, there was my measurement. It's important to remember here that you need to measure frequency down to a few hertz. Otherwise, you can't resolve it more accurately enough for the measurements we're discussing here. So I was able to do that using a spectrum analyzer. The peak here told me it to just a few hertz, and that was accurate enough for what I needed to do. Okay. The next measurement that we made was to measure the crystal frequency when it was off the PCB. You remember I took it off and I used that network analyzer with all that special software on it, and it gave me all those lovely readings which are exactly proportional, relatable to the crystal data sheet, yeah? How would I do that if I didn't have one of those things? Okay, first method, you could use a network analyzer. If you've got a network analyzer, you could set it up like in that trace where it's just showing you phase and gain. I showed you where the peak was, where the FS measurement is. The CL value you can take from the data sheet. You will need to build a pi network because the 50 ohm output from your network analyzer needs to be translated into something better, which is 12.5 ohms. And if you look at the international standard I talked about earlier on, that's 60444 part 1, it lays out exactly how to do all of that. It even tells you the proportions of the test fixture to use to make this measurement, what the values are for the pi network, and there's a ton of formulas in there, and I guess you could probably do the maths and work it out yourself. Although, I've got to be honest with you, I don't fancy doing that maths myself. The second method that I came up with, which is even harder, but if you didn't have a network analyzer, because they are expensive toys, could use a function generator, take the output from the function generator, push it across the crystal, and then take the other side from that and feed it back up to an oscilloscope, and then you could compare the two waveforms. So one from the function generator, one from the when it's been across the crystal, and you can actually, as you change the frequency on the function generator, you will be able to see, as I've tried to show in these two pictures, that the gain will change as you approach the resonant frequency of the crystal, and you'll also see the phase change. So if you were really clever, you could probably calculate where the FS point is for that specific crystal by doing that, and then I guess what you've made is a network analyzer, but you're going to manually do each individual frequency. So in theory, it should be possible to do that, although let's be honest here, that's a ton of maths and really complicated. So the third method is a bit of a cop-out, but honestly, if you're using crystals, write to your crystal vendor and ask him if he'll send you 5 pieces of crystals with numbered test data. We've all got the equipment to do that. We'll all do that for free. If you want to do these types of measurements, let me send you 5 crystals. I'll number them 1 to 5. I'll make those measurements for you, and then you can put that on your PCB and use that in your measurement system. And I'm sure whoever you're using is going to be quite happy to do the same. Yeah. Okay, so the next measurement that we made was the current dissipation and the drive level. And you'll remember that I used that current probe where I passed the wire through the middle of the probe, and it had a 1-to-1 voltage to current ratio. Yeah. The problem with trying to do this is there's lots of ways to measure current, but the first thing you need to know is that you're looking at microamps of current here. This is a really low current, so it's really hard to measure. It's also a really high frequency. It's in the megahertz range. So a lot of the op amps and stuff like that, they'll either have too low an input impedance or they'll have too high an input impedance, but they won't work at the frequency that you want. Yeah. The other problem that you've got is it's a differential signal, so you can't put a probe on one side that's grounded, because that ground will then just bleed away everything that's happening and the signal will disappear and it won't oscillate. Yeah. I really struggled with lots of different techniques for this one, and in the end, our sponsors DigiKey had a really cool little page on their website where they talked about some different methods, and I followed some instructions on there. So they talk about 3 different methods. The first one, pretty obvious, we add a current shunt resistor into the circuit. That's like a 1 ohm or a 0.1 ohm resistor, and you measure the voltage drop across that. Yeah. As I said, the problem is you've got a very small signal level and you've got a differential signal, so you're going to need an unearthed scope, which I'm not fond of that tingly feeling you get when you touch that tip of that probe myself. Yeah. So the second method that they had on the DigiKey website, which was what I was trying to do, is you can build a current transformer probe. Yeah. So here you can take a toroidal inductor and you can use it exactly like I was using with that current probe. You can run a piece of wire through the middle of the inductor back on to complete the circuit. That wire acts as a single turn on a transformer, and then you can divide the signal you get will be induced onto the turns of the inductor. You can then plug that into an oscilloscope. If you use the 50 ohm input on an oscilloscope, then what you find is that the voltage that you see on the oscilloscope, first you need to divide that by the turns ratio. So that's a 1 to however many turns you've got on your inductor. Yeah. To take that one out. And the second thing you're going to do is convert from current, to find the current, you'll need to convert from voltage into current. So you're going to divide it by the resistance, and that'll be the 50 ohm input on your oscilloscope. Yeah. Having done that, you can then take the value that's on your oscilloscope and you can see that that is the peak to peak current that's traveling through that piece of wire that you're measuring. And then you can do like we did before. You can divide that by 2 to make it a peak value, multiply it by 0.707 to find an RMS, and then work with the crystal resistance value that you've got. And I was right in the middle of doing that. In fact, there it is. There's my probe that I was trying to build there using a toroidal inductor there. You can just about see my piece of mod wire up from the crystal again up here. And I was just going to show you guys the measurement that I got, and it was all going swimmingly well when I knocked the wire, and it was rather heavy, and it snapped and it ripped the crystal and it broke it. So I'm really sorry that I can't show you a finished measurement there, but I can tell you that it was working. It was possible to do it that way, yeah, even with the very low values on a crystal oscillator. The third method that DigiKey talked about is buying a current probe. Yeah, obviously there's lots of current probes out there. Just check the frequency range and the signal level of the one that you're buying, because most current probes are only suitable for using against mains electricity at 50 or 60 hertz. Yeah. Okay, the final measurement that we made was the gain margin. You remember that we added that fixed resistor in series with the circuit, and we kept doing it and kept making sure the crystal started up. And when it got to the value, then that was our negative resistance ratio. Yeah, there's no reason why you can't do that yourself. There's nothing special about the way that I did that. There's no special instrumentation there at all. In fact, you don't even need an oscilloscope. You can just literally make sure that your system boots up, and then you know it's working. Okay. So hopefully that's given you some insights into how you can do this stuff. So final slide from me. Having talked about different ways to look at a crystal oscillator circuit, give you guys an insight into how to make some measurements and that those measurements are going to help you reduce the losses you see when you move into mass production. They're going to give you the confidence factor that you're well inside the safety margins on everything. I've been doing this type of measurement for many years, so have my colleagues. It would only be fair if I gave you a quick roundup of what I normally see when I look at other people's PCBs. So the CL value, that's our trim value, and the stray capacitance on the PCB. I can tell you that 90% of PCBs that I ever look at, the CL value could be improved. So there's almost always scope to use a different capacitor value and make the frequency more in tune with the frequency of the crystal when we manufactured it. Big question for you though is, does that really matter? Do you really need frequency to be that accurate? Yeah. If you're just using it to run a microprocessor, it probably doesn't matter. If you're doing some sort of comms system with another system, then it probably is important to you. The solution to that problem is always to change the CL value. So change the capacitors on your PCB, yeah. Drive level, we looked at drive level, remember, my drive level was really high, and I added a series resistor to bring that down, yeah. It was easy because the PCB layout had that. Honestly, when I look at other people's PCBs, it's very rare that the drive level is too high. It's possible that the drive level is too low, although that will actually manifest itself as a gain margin issue. If the drive level is really, really low, then the gain margin will be low, yeah? And that is quite often caused by using an old oscillator design. As I mentioned before, large crystals have got lower resistance, and that includes the circuits that are within your microprocessor. Sometimes that circuit was originally designed 10 years ago by the IC manufacturer. When they did the assessment of the gain that that circuit has, they were assessing it against larger crystals from that period of time. Nowadays, everything's got smaller, but nobody's really looked at the gain of that microprocessor's amplifier, yeah? Gain margin, yep, measure that on lots of people's PCBs. It's quite a common issue. It's not 50%, but it's 20–30% of boards that I look at. I could make a recommendation to improve the gain margin, yeah? Again, often caused by changing to a smaller crystal. The IC internal circuits are often legacy, as I was just saying. So they were looked at by the IC manufacturer when crystals were bigger and had a lower resistance value. And we talked about already some ways to improve that, and we could look at that by going for a lower CL, was probably the one that you guys preferred. Yeah. Okay, final 2 points here. These measurements that we've just been talking about, yeah, they don't work if your IC includes some complex automatic gain control circuit. I once saw a microprocessor that when you first powered it up, for the first 5 milliseconds, the capacitive load was really, really low, and then it switched in a bank of capacitors 5 milliseconds later. The idea was that it gave your crystal an oomph. It gave it a really large gain on that first startup, yeah? Just wait for that car to go by. So if your oscillator is doing something like that, then obviously you're going to need to take that into account, because that affects the frequencies that you're seeing, yeah? So that one caused me some problems. And finally, you're buying a crystal because you think you want a really accurate frequency. That's the most common conversation I have with people when they buy crystals. You want a really accurate frequency. You'd be surprised how many times I look at microprocessors, and in the data sheet somewhere, I find that there is in fact a register where you guys can program a value into the register, and that will correct for a frequency offset caused by the crystal, yeah? If you really need accurate frequency and the CL trim value thing is an issue for you, then I would like to suggest that you could try and do that. I realize that in production, you're going to say, oh, it's another process. I've got to assemble it and then measure it on the PCB. And that's really difficult to do in production. Well, yeah, it is, but it just might be something you want to consider because it's a function that's on your system, yeah? Okay. Well done, guys. Thank you very much. That's it. I'm done. I hope that was all right for you. Amelia, over to you.
All right, thank you very much, Nick, for presenting. Very thorough presentation indeed. We do have a few questions that have now come in. Does vibration affect the PCB?
Does vibration affect the PCB? I guess that's a microphonic question, and you're asking about whether physical vibration to the PCB affects the frequency of the PCB. The straightforward answer is not really. The more complicated answer is yes, it depends what power, what amplitude it is, and it depends what frequency it is. If it's a harmonic of the crystal frequency, obviously it will have a bigger influence, yeah. But the good thing about a PS oscillator is it's got that 180-degree phase shift in it, which does tend to block out frequencies that are outside of the window that you're looking at. I hope
All
that's
right,
okay.
thank you. Our next question here, does trim sensitivity remain constant or does it change due to an aging effect? And by that they mean, does it change over time?
Transensitivity, I think you mean what I call gain margin. Transensitivity, I think, is the an amplifier's word for the same thing. So does that change? Does an amplifier change its gain over time? I'm not aware of that one. I'm not aware of that myself. It does change over temperature, I can tell you that. And especially on nowadays, people are starting to run circuits that go up to 125 degrees as a standard temperature range. And so that's above 85 degrees. And I think in that 85 to 125, you're going to see some drop off in the gain of an amplifier, is my understanding. How's that, Amelia?
All right, that was good. We do have a couple more questions here before we run out of time. And as a reminder to our listeners, if you do have questions that don't get answered, please reply back to the follow-up email you'll be receiving within the next 24 to 48 hours. Our next question, do the crystal data sheets typically have the crystal in isolation measurements? It would be helpful if it were on the data sheet so we could skip the step of pulling the crystal off of the PCB to make that measurement.
So there you're asking about those values, the C0, the C1, the R1, the L1, that make up the motional and the holder arm of the crystal equivalent circuit, and why don't we put those on the data sheet? Well, no, they're not normally on the data sheet. The reason for that would be that if we put it on a data sheet, honestly, the reason is because if I put it on a data sheet, I then have to meet it. If I have to meet it in production, then that really limits stuff. And you saw that ESR, the resistance, where I tried to explain how it had a Gaussian distribution with a few parts that have a big outlier on it, yeah? Sorry, my boss was just waving something at the window there. That's not very helpful. So yeah, if you look at the resistance, you see the Gaussian distribution, you saw the outliers there. So if I told you what the mean value for the resistance was, I would have told you it was 15 ohms. That wouldn't have been very helpful. So that's one of the reasons why we don't do that, yeah. But who knows, maybe the future is going to change this.
Technology is constantly changing, indeed. A couple more questions here. How does the PCB coating affect the crystal?
How does the PCB coding affect the crystal? I think I don't know what you mean on that one.
The coating.
Sure. Oh, coating, sorry. How does the PCB coating affect the crystal? Okay, so that is probably, I'm guessing you're asking about, should you put a conformal coating, a lacquer, over the top of the crystal, yeah? Mixed opinions about that one. Some people do, and it's absolutely fine. I do know some really large scale manufacturers and big household name electronics guys that deliberately block the crystal from the conformal coating. Me personally, yeah, I have experienced conformal coatings that have got resistance values in the order of hundreds of thousands of ohms if you put that across the feedback loop of the resistor, that affects that resistor value. I think I had 2K, I think I had 2 meg on mine. So if you start putting 100,000 ohms in series with that, or in parallel with that, then that's going to have an influence. So I'm not a big fan of using conformal coating, although I do know people that have. I think as well, it depends what your application is. If it's a dusty, dirty, steamy environment, then it's more important to do that sort of work. If on the other hand, it's sitting in a server cabinet in a nice, well-controlled environment, then that's probably not your main priority, and you can skip that and avoid that type of problem.
Excellent. And our final question here, how do you measure the stray capacitance on the PCB?
How do you measure the stray capacitance on the PCB? Okay, so that was that slide where I had a lot of complicated maths, too many numbers on it. What I used is I know the frequency that it was oscillating at on the PCB. I know the frequency that the crystal would oscillate at in perfect conditions because I took it off and measured it on the network analyzer. And I have the trim value. So that's the value of how much the frequency changes if the capacitive load was 1 picofarad either side. Yeah. So armed with those 3 values, I can make a guess at what the stray capacitance on the PCB is, because I can make a guess at what the total capacitance value is. I can subtract the known value of the 2 capacitors that I've got in the circuit, and what I'm left with is the trim. You can use a really complicated formula and take account of the fact that that's not a linear effect, or you can do it as a linear effect because it makes the maths really, really easy, then change the capacitors and then do it again. Because once you get closer and closer to being the right capacitive value, then the non-linearity of that formula becomes less of an influence. Yeah. So you can do it, like, depends on whether you like your maths or whether you like your practical. If you like your practical, just do the maths as if it was linear. It'll tell you whether you need to go up or down. Try a value of capacitance that's down, and if that's closer, do the maths again and keep going until you get as close as you can. If on the other hand you really like doing your maths, then you can try and calculate it as a non-linear influence. Yeah, the formula was on the sheet there, and you can work it out that way. How's that, Amelia?
Oh, that is perfect. Thank you so much, Nick, for presenting for us today.
Cool. Okay, thank you. Thanks very much, Amelia. I really appreciate your help in putting this one together today.
Absolutely. And thank you to everybody who has stuck with us today and listened to this very insightful presentation. Again, if you have any questions or you think of them later, simply reply to our follow-up email that is here for you at we-online.com. And if you want to stay up to date on our webinars, you can always follow me on LinkedIn and also follow our corporate pages. Würth Electronics with a C. Don't forget to register for our next webinar. Next week, we will present improving the EMI performance of isolated power modules. Register online at www.we-online.com/webinars. And of course, don't forget to check out our new podcast as well. It's the Würth Electronic What's Up Radio podcast. Well, until next week, I'm Amelia Thompson, and I will see you soon.